Hello all, welcome to the Solocast of Firecode Tech. In these episodes, it's just going to be me, your host, Gus Gagliardi. There's going to be a range of topics, but I'm going to talk about specific technologies, installation standards, codes and how they work, as well as some other interesting topics that don't neatly fit inside of the context of a normal interview. Hello. Welcome to episode 8 of the Solocast of Firecode Tech. On this episode, we are talking about hydraulic calculations for sprinkler systems. I wanted to talk about fire pumps this week, but I realized that I had to introduce the topics of hydraulic design and how to analyze a fire suppression system to see if you are designing for the appropriate amount of pressure and flow. This is one of the most quintessential tasks for a fire protection engineer and something that's near and dear to my heart. So I wanted to go over the basics and address hydraulic calculations and when you need them, how to address the codes and standards around them, and also what are the basic steps for how to produce them. We'll see how far we get in this episode, but my goal is to take you through the entirety of how to do a hydraulic calculation and the different varietals of hydraulic calculations. So yeah, let's get started. Don't forget, if you like these Solocast episodes, you can go to patreon.com/firecodetech and get 2 of these episodes a month for the price of a cup of coffee. Also, don't forget to subscribe and give us a good review on iTunes. If you would do so, I'd greatly appreciate it. And follow us on social media so you don't miss when these great shows come out. So, I wanted to start off with what are hydraulic calculations? So hydraulics is the study of fluids and the dynamic motion of fluids. And the reason why you would have hydraulic calculations is to justify sprinkler piping configuration and sizing and the different size of sprinkler orifice / head type. And so when you need this topic is when you have already determined that you have a need for a fire suppression system in new construction or in existing construction where you are making a significant modification to a sprinkler system which requires a reanalysis of the pipe sizing and performance of the system. As just a note for this topic, there's a couple different ways you can design a sprinkler system. There's the hydraulically designed systems, which are the most frequently produced kind in modern construction. And then there's the pipe schedule system, which is how many legacy fire sprinkler systems were designed before hydraulic calculations were as common. And so the definition of a hydraulically designed system, and this is in Chapter 3 of Nfpa 13, and this particular definition is out of the 2019 version, is a calculated sprinkler system in which pipe sizes are selected on a pressure loss basis to provide a prescribed water density in gallons per minute per square foot, or a prescribed minimum discharge flow per sprinkler. And then it says, distributed with a reasonable degree of uniformity over a specified area. And so what this says to me is that there is a prescribed flow and pressure that is required for the system, and the hydraulic calculations are provided in order to justify that the system will be able to discharge this amount of water at the requisite pressure and flow. And so one of the predominant components that you need, an essential component of hydraulic calculation, is a water supply. And so you would obtain a water supply through a flow test, or you would obtain data points about the information of what a water supply is by a flow test. A flow test would be a great topic to do a show over, and I'm sure I'll get into that. But for the salient points of this podcast, let's say we have 3 data points from a flow test: a static pressure, a residual pressure, and a residual flow. And so these can be obtained through Nfpa 291. And then you can plot these out on hydraulic graph paper or paper with a 1.85 scale. And you can take a look at the distribution of pressures and flows of the water supply that's available. And so, why is this important? Understanding what is the available capacity of the water supply system that your fire suppression is using as its source of water is important to know, because if you are above this curve that is made by plotting the static pressure, the residual pressure, and the residual flow, then you were not able to use the sprinkler system in its design manner. You're going to need either a fire pump or a fire protection water storage tank. And so this is a little bit hard to explain because it's a very visual, a graph of hydraulic water supply is a very visual thing. But I just wanted to mention that. And so a pipe schedule system is basically just based on a set of sizes. And so the definition from Chapter 3 is a sprinkler system in which the pipe sizing is selected from a schedule that is determined by the occupancy classification, and in which a given number of sprinklers are allowed to be supplied from a specific size of pipe. So a great place to look if you're wondering about information on hydraulic calculations, and I haven't said this yet, but all this information about how to calculate a fire sprinkler system is through the lens of codes and standards in the U.S. So International Building Code, and then followed by Nfpa 13, and then so big chapters in Nfpa 13 for hydraulic calculations are the definitions chapter and also plans and calculations in the 2013 version, that's chapter 23. And so place where you can see more information about pipe schedules and how many sprinklers equals what pipe size is in 23, where they talk about for the specific hazard, how in the specific type of pipe, how many sprinklers can you get on each size of line. So it starts off at 2 sprinklers on 1-inch line, and then if you have more than 2 sprinklers, if you have 3 sprinklers, you have to have on a line, you have to have that on, and this applies to lines or mains. You have to have it on 1.25 inches, and so this table goes up and up and up. And so another good point to talk about is hazard determination. And so what does hazard determination look like? So let's go over a couple of definitions for the different hazard types and when you would need these. There are a couple different types of preliminary hydraulic analysis or hydraulic analysis. And one of the most common ones that I've seen is the density area method. And one of the first steps in calculating a fire sprinkler system for the density area method is determining the hazard classification. And so we have light hazard, ordinary hazard 1 and 2, and then extra hazard 1 and 2. And so as you can imagine, light hazard is the least hazardous, which requires the least amount of water, and extra hazard 2 is the most hazardous and requires the most amount of water. And so this is density area is the most simple method of hydraulic calculations. There's also more specific methods for storage sprinklers like ESFR sprinklers or CMSA sprinklers that don't follow the standard conventional rules. And so taking a look at those, that they're specific, the core tenets of what it means to address the hydraulics of it, which is verifying the pressure and flow is adequate, is the same, but the way that you select how many sprinklers you flow and some of the other factors can change. So let's move forward with the discussion of a typical area density approach. So I'm much more used to the approach and how it's laid out in Nfpa 13. In the earlier versions of Nfpa 13, as of 2019, they've totally reconfigured the standard. I'm not as comfortable with that methodology. Maybe I'll do a comparison in the future, but for now, I'm still taking a look at it through the lens of the 2013 edition. So right now we're looking at chapter 11, which talks about the design density and area method and how to model this approach. The 2019 edition of the standard lays out the design process a little bit more linear in the way that the book approaches it. Yeah, hazard determination is one of the first steps in the process. And so it says classification shall be as follows: light hazard, ordinary hazard, extra hazard, special occupancy provisions. They give a caveat for storage applications and how those are not covered as a part of this design approach. And so it gives a couple of options for how you would determine it. It says occupancy hazard fire control approach and special design approaches of chapter 11, storage design approaches of chapter 12 through 20, special occupancy approaches of chapter 22. So what this is telling you is you can use the standard density area approach of chapter 11 if you have storage design, so that's high piled storage or appreciable amounts of storage in excess of a quantity that's allowed in NFPA 13, you would use chapter 12 through 20. Or if you have a really special case occupancy, say you have a sprinkler system for a marine scenario, say you have a riverboat with a fire sprinkler system, then you may want to look in chapter 22. Or if you have a really kind of unique design approach, then you want to look in chapter 22. And so really at this point in the process, you want to take a look at where your lead-in for your sprinkler system is going to come into the building, and then you want to, analyze where your most remote, most hazardous area of your building is. This is going to help you determine where your remote area is going to be and help you figure out where the most demanding pressure and flow area of your building is. And so there's, of course, many scenarios in which you'll have to do multiple hydraulic calculations in order to justify your piping and sprinkler head configuration in multiple areas. But let's just, for instance, say that you have a square building and you come into the southwest corner of the building, and the northeast corner of the building is your most hazardous area, and it's an ordinary hazard 1 area. Based on your hazard category, you need to determine the minimum amount of area you can calculate with your required density in order to determine the flow needed. If you look at the charts on 11.2.3, water demand requirements, hydraulic calculation methods, you'll see a very interesting table. Figure 11.2.3.1.1, density area curves. This is where the term the density area method comes from. And so you have a linear line sloping downwards, and they have one for light hazard, they have one for ordinary, and 1 and 2, extra 1 and 2. And so from here you can get your first sense of some different factors for density. And when I say density, I mean density of water per square foot. And so there is a line that slopes downward. And so we take a look at ordinary 1 for the process we're speaking of. And so there's an area of sprinkler operation, and the beginning of the line starts at, you could take a look at 0.1 GPM over 4,000 square feet, and then this line slopes all the way down to the second point is 0.15 GPM at 1,500 square feet. And so basically there's an acceptable range of densities and areas allowed for ordinary hazard 1 that you can use to calculate your system demand flow. And so you choose your remote area, and now we have to choose the density and the area of operation. So you could select 4,000 square feet at 0.1 GPM, but I've never in my whole history of my design experience seen somebody select towards the top of this line. They always select near the bottom of what's allowed, 0.15 over 1500, which the reason why you would do this, there's a you could essentially be more conservative or less conservative, or you could say more cost effective. Um, and so 0.15 times, or let's just go with 0.1 times 4,000 is 400 gallons per minute. And then 0.15 times 1,500 is 225 gallons per minute. So you're flowing, you know, another 175 GPM for the same classification of hazard. It just doesn't happen because more flow equals needing bigger pipe sizes, bigger sprinklers, and more costs along the way. So in the common convention, you're gonna pick the lowest point of the curve unless there are some design guidelines in place that are going to make it essentially required to select somewhere else in that range. And so there's some area adjustment factors you might have to use. If you have a dry system, you might need to add a multiplication factor to increase the area you have to take a look at by zero point 0.3. If you have a roof that is severely sloped, you might have to add a factor that increases the area in which you need to analyze the sprinkler system by, I think it's from like 0.1 to 0.2. I forget exactly how much. And so that is a factor that could also change the area in which you're looking at. And so conversely, there are some reductions that you can apply if you have light or ordinary hazard occupancies with specific ceiling heights, flat ceiling heights, and so you can get a quick response reduction up to, it looks like 40%, and you see this used very commonly because for an office space with a 10-foot or 8-foot ceiling, you would be able to take this exception, and it would be advantageous because you could lower the water required, and thus the piping and sprinklers could also be reduced, and you could be beneficially compensated for this reduction in flow. And so after this, you in regards to flow. So everything we talked about so far has been in regards to flow. We haven't yet started to talk about pressure and how to analyze pressure of the system. So as a quick recap, we determined hazard, we've determined remote area, and we have taken a look at the area and density required, and we have adjusted for allowance factors like dry pipe and we've adjusted for ceiling slope and let's just say it's since it's ordinary hazard 1, let's say it is just a small utility shed with the minimal combustible loading in it. Don't think we're going to make it all the way through to pressure in this session, so let's just say that talk about the last factor, which would for flow, which would be hose allowance for extra fire department connections. And so you have different hose stream allowance and duration requirements for the differing hazards, and so it ranges from 100 to 500 gallons per minute, and so 250 for ordinary hazard, and so you would have to add this. So if you're doing preliminary hydraulics and you know that you have an ordinary hazard occupancy and you want to get a sense of how much flow you're going to have, you can, take your 1,500 square feet. You can put a safety factor on that if you would like. You'd say like times 1.3 and say 1,800 square feet. Multiply that by 0.15 GPM per square foot. That would give you 270 GPM, and then you would add an additional 250 GPM for the hose stream allowance. This would give you an approximation of what kind of flow you would be expecting for an ordinary hazard occupancy. Just through experience and through repetitions, I've seen flows for ordinary hazard can range through about like 500 to maybe the upper of what you might expect would be like 800 or 900 GPM if you have an ordinary 2. And so this would be in line with what I've seen and what I would expect. Anyways, well, that wraps up flow for the most part. Doesn't cover all of what could be considered, of course, but we're coming up on a lengthy one here. And so we're going to sign off. Thank you guys so much for listening. And don't forget to subscribe. And if you're interested, go check out the Patreon. All right, thanks, guys. Thanks for listening, everybody. Be sure to share the episode with a friend if you enjoyed it. Don't forget that fire protection and life safety is serious business. The views and opinions expressed on this podcast are by no means a professional consultation or a codes and standards interpretation. Be sure to contact a licensed professional if you are getting involved with fire protection and or life safety. Thanks again, and we'll see you next time.